Okay, here's the computer set up here. I must not be talking very loud. I know it's on the beach, but I think it was the wind. Anyway, we got a flat screen finally, which is nice. We like flat screens. There's the Rickettos. Okay. This is Jim's library. Jim doesn't have to go to the library for anything technical. He's got his own. You name it. Let's see what we got here. You want to learn about pulse, digital, and switching waveforms? You got it. You want to learn about whistlers and related ionospheric phenomena? You got that. Well, here is a good book. Probability, random variables, and stochastic processes. That sound like fun? What we got here? Whoa, got Judy Collins. Now that's an LP, vinyl, pristine. And guess what? Judy has a house here in Lincoln City. So someday I'm going to run into her somehow and get her to sign this. And then will I sell it on eBay? No way. So much for Jim's library. But, okay. Has an addition. I thought I'd put this on. You saw a book that said, well, let's take a look at it. Whistlers and related ionospheric phenomena. And you probably wonder, what the hell's a whistler? Well, the first thing to do is show you. Now this graph, the frequency is plotted from top to bottom. So you can see 2 kilohertz on the top, 1 kilohertz towards the bottom. And time is to the left. So you can see how frequency changes with time. Now the first thing you're going to see is a lightning strike. And that's just a big vertical thing. Well, let's just do it. Alright. That's the lightning strike. That's the whistler. I'll look at that again. Okay, let's freeze frame it this time. Okay, just notice the whistler starts out at a high frequency and then the lower frequencies come along. Okay, I'll give you a brief explanation. First of all, you might want to go to this site here. I'll let you do the research. But basically a whistler is that it's caused by lightning. It's a radio wave, a very low frequency radio wave that goes out, and it follows a magnetic field line of the Earth into the other hemisphere and then bounces back. You noticed in this one we had two whistlers. There was a double one. So it must have bounced back again and then back. In any kind of waveform, if it's modulated, you look at the modulated part, and that's called the group velocity. The waves that make up the modulated part are their speed is called the phase velocity. But the simplest form of a modulation would be just a simple pulse, which contains a lot of frequencies. Okay, as the pulse travels along, its speed is the group velocity. But in the magnetosphere, there's what's called dispersion, so that the higher frequencies get ahead of the lower frequencies, so it tends to smear out the pulse. So that's why you hear the high frequencies first and then the low frequencies. This is exactly opposite to the way light waves behave in the atmosphere. In fact, the lower frequencies travel faster than the higher frequencies. So it's just the opposite. In other words, the magnetosphere has a negative index of refraction. You can put it that way. So here's another site you might want to go to. And I'll let you do the rest of the homework. But there anyway, at least you know what a whistler is. I can't whistle anymore.